everyone. This is the fourth, or sadly second to last video in my geometry week series. And today I decided that I would do this problem. It's a Sangaku, which means it's one of those problems that are holy tablets that appear in shrines throughout Japan. Now I don't remember exactly where it was from or when it was from, but I'll link down below in the description to the file in which I found it. There's probably 29 or 30 or 30 problems in that file, including this one, as well as all the solutions. So let's see what our problem is. For this problem, we have a black semicircle in which a black circle is inscribed such that it has a diameter equal to the radius of the semicircle, and then these two line segments right here are tangent to the black circle, and we have connected them to the opposite side, to the opposite end of the diameter, and we have inscribed these two circles. Although this one looks more like a mashed potato to me, it still is a circle, and we want to find the ratio of their radii. Namely, we want to find the ratio of R1 to R2. But first, before we solve the problem, I would like to prove a quick lemma that we will need throughout the problem. So our lemma will be that if we have some quadrilateral like this ABCD, where this angle is theta, this is A, this is A, this is B, and these two are right angles, then B will be equal to A times the tangent of theta over 2. And now we'll prove this lemma. So put down the PF. Okay, so we know that the sum of angles in a quadrilateral is 360 degrees or 2 pi radians. So this means that angle A plus angle B plus angle C plus angle D will be equal to 2 pi. But then B is equal to angle B is equal to pi over 2, angle C is equal to theta, and angle D is equal to pi over 2 as well. So we can move these three terms to the right hand side to give us that angle A will be equal to, pi over 2 plus pi over 2 is pi, 2 pi minus pi is pi, and don't forget to subtract theta. Therefore, angle A will be pi minus theta. And now we will connect B and D, and we will let BD be equal to x. So let BD be equal to x. And now we have two triangles in which we can apply the law of cosines. So by law of cosines, so applying it on triangle ABD, we get that x squared is equal to b squared plus b squared, which is 2b squared. Hold on, let me redo these exponents. Minus 2 times b, which is 2b squared, cosine of pi minus theta. And now I would like to factor out a b squared. So this will give us 2b squared times 1 minus the cosine of pi minus theta. But then the cosine of pi minus theta is just minus the cosine of theta. You can easily verify that using the unit circle or something. So this will be 1 minus minus, which is plus cosine theta. And now, if we apply that same law on triangle BCD, we get that x squared is equal to a squared plus a squared, which is 2a squared, minus 2 times a, which is 2a squared cosine theta. But then, as we did earlier, I would like to factor out a 2a squared to give us 2a squared times the quantity 1 minus cosine theta. And now we have two equivalent expressions for x squared, which we can set equal to each other. So this gave us that 2b squared times 1 plus cosine theta, 1 plus cosine theta, is equal to 2a squared times 1 minus cosine theta. And now we can divide both sides by 2, and then we will divide both sides by 1 plus cosine theta to leave us with b squared is equal to a squared times 1 minus cosine theta over 1 plus cosine theta. But then, what is 1 minus cosine theta over 1 plus cosine theta? Well, it is exactly, by the half angle identities, tangent squared of theta over 2. So a squared tangent squared theta over 2. Oh, that 2 was not so nice. And then we can just take the positive square root on both sides to give us that b is equal to the tangent of theta over to a times the tangent of theta over 2, which is exactly the result that we are seeking for our lemma. Therefore, we can put a QED on this one. And now that we've proved our lemma, I will clean up this board and we will start actually solving the problem. Okay, so now that I've cleaned up this board, we can finally start solving our problem. So, first of all, I would like to observe that our two triangles right here and right here, since they are inscribed in a semicircle, will be right angles, so right triangles. So this will be a right angle as well as this. And now I would like to draw draw the center of our circle. Sorry, I erased a little bit of this. Okay, and now you will connect it to here. So we'll go through here. As I probably already said, I'm pretty perfectionist when it comes to geometry. And we'll draw this one right here. So we will call the radius of our black circle R. This is R, this is R. And then, since the radius of our black circle is R, its diameter will be 2R. But that is exactly the radius of our semicircle, so this will be 2R and this would be 2R. And now I would like to observe that these two lengths are exactly equal by the principle of equal tangents. Therefore, this will also be 2R. And next, I would like to call this angle right here to be alpha. Let me review that alpha. And now we can see that we have a quadrilateral right here, which is exactly like the quadrilateral in our lemma. So we can apply this lemma to this quadrilateral to find that R will be 2R times the tangent of alpha over 2. But then, dividing both sides by R, and with cancelling the r's and dividing both sides by 2, we get that the tangent of alpha over 2 is equal to 1/2. And now I would like to use this information to figure out the sine, cosine, and tangent of alpha. And here's how we are going to do it. We know that the tangent is nothing but the sine over the cosine, so this will be sine alpha over 2 over cosine alpha over 2 is equal to 1/2. And then we'll cross multiply to get that 2 sine of alpha over 2 is equal to the cosine of alpha over 2. And now I would like to square both sides, so this will give us 4 sine squared alpha over 2 is equal to cosine squared of alpha over 2. And now here's what I would like to do. I would like to add sine squared of alpha over 2 to both sides. And here is why. On the left hand side, we'll get 5 sine squared of alpha over 2. And on the right hand side, we'll get cosine squared of alpha over 2 plus sine squared of alpha over 2, which is just 1 by the fundamental theorem of trigonometry. And then we can divide both sides by 5 to find that the sine squared of alpha over 2 is 1/5. And now, I would like to make use of the double angle identity for the cosine. So I would like to recall that the cosine of 2 theta is equal to cosine squared theta minus sine squared theta. But then, what is the cosine squared? Well, the cosine squared is nothing but 1 minus the sine squared, again by the fundamental theorem of trigonometry. Therefore, substituting this in and collecting like terms, we get that this is just 1 minus 2 sine squared theta. And now, we can make use of this identity to find that the cosine of 2 times alpha over 2, which is alpha, is equal to 1 minus 2 sine squared of alpha over 2, which is 2/5. But 1 minus 2/5 is just 3/5. So the cosine of alpha is 3/5, which means that the sine of alpha is equal to 4/5, and therefore the tangent of alpha will be 4/3. And all this means that our two right triangles are in fact 3, 4, 5 right triangles. That is interesting in its own right, but we don't care about triangles, we care about our two circles. So now now we will find our R1. So we know that because of this triangle, this angle will be pi over 2 minus alpha because of this angle in the triangle and everything. And then we know that this is R1 because it's the radius of our red circle. And we know that this is tangent, everything is tangent. And by the principle of equal tangents, this will be equal to 2r as well. And now, again, we have a quadrilateral that is exactly like our lemma. Therefore, we can use our lemma onto this quadrilateral to find that R1 will be equal to 2r times the tangent of pi over 2 minus alpha all over 2, which is pi over 4 minus alpha over 2. But then, the tangent of pi over 4 minus alpha over 2 is using the tangent angle addition identity, which I left as an exercise to the reader to prove a few videos ago. I hope you did your homework. So this will be 2r times tangent of pi over 4, which is 1, minus tangent alpha over 2 all over 1 plus tangent of pi over 4, which is 1, times the tangent of alpha over 2. But then, what is the tangent of alpha over 2? Well, it is just 1/2. So this will be 2r times 1 minus 1/2 over 1 plus 1/2. And now, let's see. 1 minus 1/2 is 1/2. 1 plus 1/2 is 3/2. And 1/2 over 3/2, the 2's cancel out, giving us only 1/3. So this will be 2r over 3. Therefore, we can say that R1 will be equal to 2r over 3. Good. And now we'll start finding R2. And to do that, I would like to draw this whole entire radius. It will go through the center of R2, this point of intersection, the center of our black circle, and the center of our circle with radius R1. And now, what I would like to do is, I would like to find this length right here. So, this length will be the length of, well, first we'll call that length D, and then the D will be equal to the length of the entire radius minus this length right here. So our D will be equal to the full radius, which is 2r, minus this length, which is r2, because it's the radius of the circle, so r2 minus this length. But what is this length? And to do that, we will use some trigonometry. So we know that, let me do it in red. Okay, so here we have pi over 2 minus alpha, which is this angle right here. This is a right angle. This is 2r. And now, consequently, this angle will be alpha. And we can use trigonometric ratios to find that this side will be 2r cotangent of alpha. But what is the cotangent of alpha? Well, it is just the reciprocal of the tangent of alpha, which gives us 3/4. So 2r times 3/4 is 3r over 2. So 3r over 2, which means this length right here is 3r over 2. Therefore, we will have to subtract 3r over 2 to find our D. But then the r term simplifies down to r over 2, and we get minus r2. And now we can see that these two triangles are congruent since everything is symmetrical, which means that this angle will also be pi over 2 minus alpha, just like this angle. And now we know that this angle will be alpha because it's a right triangle and everything. And since these two are vertical angles, they will both be equal to alpha. So now here we have a right triangle, since this is a point of tangency. And I will zoom in onto that triangle. So we have our right angle here. Let this be a right angle. So let me do it again because it wasn't good. Okay, so this is alpha, this is R2, and this is D. And from this picture, we can easily conclude that the sine of alpha will be R2 over D. But what is the sine of alpha? Well, it is just 4/5. So this will be 4/5. And then we can just cross multiply to get that 5R2 will be 4D. But D is exactly this length right here. So this will be 4 times R over 2, which is 2R, minus 4R2. And then add 4R2 to both sides. We get 9R2 is equal to 2R. Not RR, it's 2R. Like this, so 2R, and then divide both sides by 9, we get that R2 is equal to 2R over 9. And now we are ready to answer our main question: what is the meaning of, what is the ratio of the radii of our two circles? And now we can just substitute our values in terms of R in, so this will be 2R over 3 over 2R over 9. And then this will be equal to, the 2 r's cancel out, and we'll be left with 1/3 over 1/9, which is 9/3, which is 3. Therefore, the ratio of the radii of these two circles is exactly 3, no matter what the circles are. So, as I said earlier, if you want more problems like these, I will leave down in the description the file in which I found it, which has 30 or more problems like that. And this problem, we didn't exactly ask the R1 over R2. What we originally asked was express the diameter of this circle and the diameter of this circle in terms of the diameter of our black circle. But I chose this variation because the answer was nicer. Instead of leaving us with an expression with variables, we had an actual number, which is nice. It's just 3. So this is your video. Thank you guys for watching this video. Don't forget to share, and I'll see you in the next video. Bye.